So in the last video, we discussed the relationship between pi0 and h0, and now we're going to consider instead pi1 and h1, which is a bit more complicated. Okay, so firstly, we need to recall this definition of the abelianization of a group G. So remember, if you've got a group G and some elements x and y, then the commutator of x and y is xy, x inverse, y inverse. And you can consider, well, we use the word multi-commutator for an element that's a product of commutators, some finite list of commutators. And we proved that the multi-commutators form a normal subgroup of G, and we take the quotient by that normal subgroup, then that's what's called the abelianization of G. So that's basically the minimal way to take a quotient of G and force it to be commutative. So the theorem is like this, that if we've got a connected simplicial complex K and a vertex A of K, then we can consider the first homology group H1K, or alternatively we can consider the first homotopy group, the fundamental group, pi1 of the geometric realization of K with base point A. And well, those H1K is always abelian, and pi1K is sometimes not abelian, so those two things certainly can't always be the same. But what's actually true is if we take this pi1, the pi1 of the geometric realization of K, and then we abelianize it, then that's always going to be isomorphic to H1K. That's provided that K is connected, like we say. So we're going to give a partial proof of this. So most of the main ideas we're going to discuss. So we're going to start like this. For each vertex x, we're going to choose a path ux, which starts at the base point A and ends at x. Okay, and that's going to be possible because we're assuming that K is connected. And, which doesn't matter too much, but we can take it to be like a path, a sort of abstract path that goes along the edges. Okay, so now suppose we've got some arbitrary edge E from x to y in K. So that gives a path from x to y in the geometric realization, and then we can compose that with the ux and the uy, or we do ux first and then we go along E and then we go backwards along uy, so that's uy bar. So that gives us a loop, which is an element of pi1 of the geometric realization. And then this abelianization, by definition, that's a quotient of pi1. So it's got this loop ux star e star uy bar, the corresponding coset that's of that in the abelianization. So that's an element of pi1 ka ab, and we're going to call that element alpha naught of this edge xy. Okay, so now suppose we've got a general element of the group C1K. So remember, C1K is essentially the free abelian group on the edges. And so we've already defined alpha 0 EI for each of these edges, and we're going to define alpha 0 of U to be the product of alpha 0 EI to the power Ni. Okay, so there's a little bit of a kind of glitch here because we write the group operation in C1K as addition and the group operation in pi1K as multiplication. So we want to make alpha 0 into a homomorphism. It has to convert addition to multiplication. So that's so the sum over I of Ni EI becomes the product over I of alpha 0 EI to the power Ni. Okay, so this now gives us a homomorphism alpha 0 from C1 to pi1. And notice that there could be we've just kind of blithely written this product here. And if we try to write a product expression like that in an arbitrary group, then you can run into trouble because you don't know which order to multiply the factors in. But we've made an abelian group here. We've taken this quotient by multi-commutators to force pi1k to be abelian, and so in this abelianization, it doesn't matter which order we take the factors in. So this alpha 0 behaves in a straightforward way. So now suppose we've got a two simplex x, y, z in K, and then so that gives us a one chain D2 of x, y, z. And the claim is going to be that if we apply this homomorphism alpha 0 to D2 of x, y, z, then we just get the identity element. To prove that, well, let's remember what is D2 x, y, z. So we get that's yz minus xz plus xy. Yeah, in the first term, we leave out the x, the second with a plus sign, then we leave out the y and have a minus sign, then we leave out the z and we have a plus sign. And we want to rewrite the middle term minus xz as plus zx. Okay. So then we apply alpha 0 to that. Yeah, so you get for this yz term, you get uy, then yz, then uz bar. For zx, you get uz, then zx, and then ux bar. And for the xy term, you get a ux, then xy, and then uy bar. Okay. But remember that so uz bar is the inverse to uz. So this inside here, we've got uz bar star uz. That's that can be cancelled. And similarly, ux bar is inverse to ux, so the ux bar star ux, that can be cancelled. And we're just left with this uy star yz star zx star xy star uy bar. Okay, now notice that this middle section here, yz star zx star xy, okay, that's all happening inside the simplex xyz. Okay, we're just kind of going around the three edges of this triangle. And an XYZ is a simplex in K by assumption, so it's a kind of filled-in triangle, and so it's kind of convex. We can, and this path here, it goes from Y to Z, then to X, then back to Y again. So it's just a loop at Y, and so we can just contract it by a straight line homotopy to the constant path at Y, just moving everything across this simplex XYZ. Okay, so this middle term here, YZ star ZX star XY, that's has a pinned homotopy to the constant path CY. Okay, but remember, if this kind of path join operation, constant paths act as kind of identity elements. So this we can leave out the CY; it doesn't make any difference. So we've just got a UI star UI bar, and then again UI star UI bar is kind of inverse to UI. So this is kind of running UI. Remember, ran from A to Y, and then we run back again. So the inverse property means that that's pinned homotopic to the constant path CA, which is the identity element of pi 1. Okay, so we conclude that this alpha 0 d2x yz is actually the same as the identity element as we claimed. Okay, so now let's think about an arbitrary element of this group B1K of boundaries. So remember, B1K is the image of D2, so it's generated by elements of the form D2 sigma or D2XYZ, or we could write sigma for a general 2 simplex XYZ. Okay. And we've shown that alpha 0 sends each D2 sigma to the identity, so it will send anything in the subgroup that they generate to the identity as well. So alpha 0 is sending the whole of B1K to the identity. So that means in the usual way that we get an induced homomorphism from the quotient group. We take the quotient by this subgroup B1K because alpha 0 is sending B1K to the identity. The value of alpha 0 as an element here just only depends on the coset. So we get an induced map from the quotient group. And that's actually from the whole of C1K mod B1K. We don't actually care too much about the whole of C1K. We're really only interested in Z1K, which is a subgroup. But because B1 is contained in Z1, which is contained in C1, we could just restrict this induced map and just down and only consider how it acts on Z1K mod B1K instead of the whole of C1K mod B1K. And that Z1K mod B1K, by definition, that's the first homology group H1K. So now we've got a homomorphism from H1K to this abelianization, which we're going to call alpha. Okay, so we've at least got a homomorphism, and we want to claim that it's actually an isomorphism. So let's start trying to build a map in the opposite direction. Okay, so opposite direction, we need elements of the of this abelianized pi 1. They're represented by loops, and we could have an abstract loop, for example, just corresponding to a list of vertices like this, starting with U0 is A, U1, U2, it's UR minus and UR, where each UI, UI plus 1 is an edge. So that's an abstract path from A to A. And if you've got an abstract path like that, then we could just take the sum of all the edges. Okay, that gives us an element of the chain group C1K. And and we've seen this kind of thing before because everything lines up neatly when you take D1 of this. most of the terms are going to cancel out, and you just get kind of the end term UR minus the initial term U0. But by assumption, this was an abstract loop starting and ending at the same point A. So this D1Z is UR minus U0. They're both equal to A, so D1Z is actually just 0. So this element Z, it's actually satisfies D1Z is 0. In other words, it's a cycle, an element of the group Z1K. And so we have a homology class, which is just a coset of this Z, coset Z plus B1K. So that's an element of the group H1K. Okay. So this is kind of beginning to give us a map from pi1 to from the abelianized pi1 to H1, but we need to do a bit more work. I mean, this is only kind of works for abstract paths, and not every you can have paths that kind of wiggle around a lot and don't go along the edges, and they don't count as abstract paths, and it's not so clear what to do with those. Turns out, I mean, there is a version of pi1, this abstract pi1. I mean, we proved this kind of thing for pi0, that pi0 abstract was the same as pi0. And there is a kind of abstract version of pi1 as well. There's a bunch of details to do for that, which we're not going to go through. But by filling that in and doing some more work along the same lines, we get a map, let's say beta 0 from the abstract pi1 to H1K. And there is this theorem that we're not going to prove that the abstract pi1 is the same as the normal pi1. Okay, so if we believe this exists and it's a homomorphism, well, then it's going to send every commutator in pi1 to a commutator in H1, but H1's already abelian, so the commutators in H1 are just trivial. So, and similarly, any product of commutators gets sent to a sum of commutators. That's also trivial. So this is sending multi-commutators to the 0 element. And so because of that, that means it factors through the abelianization. And so we get a homomorphism beta like this from the abelianized pi1 to H1 in the opposite direction to the alpha that we produced up here. And again, there's a certain amount more work to do that we're not going to discuss, but you can check that this alpha is inverse to beta, so we have an isomorphism as claimed.